A very good afternoon to all the lecturers. We are from CE3-G32. In this September 2020 semester, our topic for integrated design project is methanol production using steam methane reforming SMR process. Next. In the executive summary, we have summarized all the important points in each chapters. First of all, we have to introduce what is methanol. Methanol is the simplest alcohol that is usually derived from natural gases and is very widely used in the industry recently. In this integrated design project, we were asked to design, simulate, and analyze a methanol production plant to produce methanol of 95% purity. For drawing and designing process, we decided to use the visual paradigm software. And for simulation process, we decided to use the HYSYS software. The suitable plant capacity that we propose is 3,000 tons per day from our research. After that, we analyze the VLE graph, which is the vapor-liquid equilibrium graph, as well as phase envelope, as indicated in part thermodynamic, using HYSYS, and then we perform the flash calculations. For the separation process one part, we have decided and used optimum reflux of 0.219 because the number of theoretical trays used is the least, which is 4+1 reboiler. Next, I'll pass the floor to Siti Aisha.
Okay, so methanol is a chemical substance which has a chemical formula of CH3OH. It is also known as methyl alcohol or wood alcohol. It is a polar molecule because it has a methyl group which is connected to the hydroxyl group. Methanol can be produced industrially by combining carbon monoxide and hydrogen gas directly. So, characteristic of methanol includes it is a colorless gas, volatile, and it is also a simple alcohol. It has a low flash point, which makes it very flammable. And as previously mentioned, it is a polar molecule. Methanol is poisonous to human health too. So next, I will pass to Darusha.
I will talk about the applications of methanol. Nowadays, the function of methanol is very wide as it can be used to manufacture safe and biodegradable biodiesel fuel which emits less harmful air pollutants. It also can be used in thermal applications such as industrial boiler. Besides, methanol can be a feedstock for synthesis of various chemicals for producing foams, adhesives, and solvents. Next, I will pass the floor to Amalina.
For the chapter 2 process flow diagram, we analyze the selection of instrument of methanol production process based on the problem statement given for the IDP. For the mass balance part A, in methanol purification, unit D103, we start with the value as 11, 3,000 times per day, which was analyzed from the market analysis. From the problem environment IDP, our group was given the value of F 0.97 and the value of SS10 is calculated from the mass balance, which was 3,095.78 ton per day. We also did the overall balance, which for the system at the slide that will give value of S12 92.78 ton per day. Water methanol balance is calculated to get the mole fraction of water, which is 0.8367, and methanol, which is 0.1633. For the part B, which is syngas recovery unit D103, we did the overall balance to get the value of S6, which is 13,382.30 ton per day, and then substituted again in the balance to get the S7, which is 10,289.52 ton per day. Each composition is calculated to get the mole fraction. I will pass the floor to Aisha.
Okay, so since 90% of both CO and H2 is recycled back to stream 8, molar flow of CO and H2 both can be calculated, which is 3839.13 kg mole per hour and 58049.52 kg mole per hour. Next, by assuming S8 is consisting of CO, CO2 and H2, mass balance can be performed. Therefore, by using appropriate equations, we can calculate that for S5 is equal to 19707.31 kg mole per hour, epsilon 1 equals to 3175.57 kg mole per hour, epsilon 2 is equals to 552.59 kg mole per hour, and CO2 is equals to 346.73 kg mole per hour. So we will do checking for S5, epsilon 1 and epsilon 2 for water and hydrogen balance, and in the result we will get a percentage difference of 2.43% and 0.25% respectively, which is both less than 5%. Therefore, both are valid and accepted. I will pass to Darusha next.
For condenser, in order to find its overall balance, we can take the mass fraction and mole fraction value for stream 3 and stream 4 from HYSYS. As we can see, since the problem statement mentioned that 95% of the H2O in stream 3 is to be removed through stream 4, we can calculate that stream 4 is equals to 0.1091 S3. So in the overall balance, by performing appropriate calculation, we can find that S3 is equals to 22,120.68 kilomole per hour, and then we can get that S4 is equals to 2,413.37 kilomole per hour. Next. For the reforming reactor, by performing the appropriate calculation, we can get that epsilon 2 is equals to 900.31 kilomole per hour. And for the carbon monoxide balance, we can find that epsilon 1 is equals to 4,499.34 kilomole per hour. For the methane balance, we can get that S1 is equals to 5,291.26 kilomole per hour. And for water balance, we can get that S2 is equals to 7,939.10 kilomole per hour. For the checking value of epsilon 1 and epsilon 2, we can get that percentage difference is 0.76%, which is less than 5%. Hence, the hydrogen balance is valid and acceptable. Next.
Chapter 2 mass balance. In conclusion, 5291.26 kilomole per hour of methane and 7,139.10 kilomole per hour for water are needed to be applied in order to produce 3,000 tons per day of methanol with 95% purity. For the justification, firstly, percentage of water removal is 95.02%, which is proven. Hence, the value of flow rate is justified as well as the effectiveness or the efficiency of the condenser in removing 95% excess water. This efficiency can be further justified as one day Dong and Byung 2013 stated that at temperature 50 degrees Celsius, the composition of water from the reforming reactor needs to be removed to less than 0.6 mole%. Since our temperature is 43.76 degrees Celsius, which is quite close to the literature temperature, hence the theory can be accepted.
For the chemical engineering thermodynamics 2, which is chapter 3 part, we have understand some concept. First of all, the VLE vapor-liquid equilibrium is a state of coexistence of liquid and vapor phase. Hence, the VLE graph will describe the relationship as well as the distribution of chemical species between vapor phase and liquid phase. In fact, the VLE data can be determined experimentally by simulation or the calculation with the help from Dalton's law, Rao's law, and Henry's law. Two major assumptions are needed to be applied in our case, as we assume the vapor phase of methanol and water is an ideal gas, which is low to moderate pressure. Secondly, the liquid phase of methanol and water is an ideal solution in which they are chemically similar. Next. Next. For the first part, which is the VLE graph of mixture in D103, the graph 3.1.1 and graph 3.1.2 are the XY graph and PXY graph at constant temperature T equal to 60 degrees Celsius. Next. For the part B, which are the phase envelope of mixture in the same unit D103, the first two graphs, graph 3.3.1 and 3.3.2, are the pressure against temperature and pressure against molar volume graph for bubble point. For the next two graphs, which are graph 3.3.3 and 3.3.4, are the pressure against temperature and pressure against molar volume graph for dew point. Next. In the final chapter, which is the separation process 1, we are asked to design and to calculate the theoretical number of stages for our distillation column. We have been given the extant temperature to be 60 degrees Celsius as given in the problem statement, and the fraction of feed that is vaporized in distillate S11 as well, which are 0.97. We have three assumptions in this chapter. The first one is the inlet flow rate F is equal to 4252 kilomole per hour from the mass balance chapter 2. Also, the mass fraction of methanol in stream S11 is equal to 0.95, and the mass fraction of methanol in stream S12 is equal to 0.1633. Next. Based on our mass balance in chapter 2, we have acquired the composition of methanol and water in both stream 11 and stream 12. And by using the values and substituting into the Antoine equation, we got the value of PA saturation is equal to 83.989 kilopascal and PB sat is equal to 20.007 kilopascal. By using the formula of relative volatility, we got the value of 4.198. We sub the value of 4.198 into the equilibrium curve equation, and we got the complete equilibrium curve equation. And after that, by using the interval of 0.2 from 0 to 1, we got its own YA values respectively to plot the curve of equilibrium. Next. In order to determine the number of stages, we decided to use a graphical method, and the following steps were done. Firstly, we determined the Q line using the equation of Q equal to 1 minus X, and sub the value of Q inside the Q line equation to get the complete Q line equation. After that, we find the R mean, the minimum reflux ratio, to find the intersection between the equilibrium curve and Q line. And the intersection point is known as the pinch point, the coordinate of X prime and Y prime. We substitute the value of X prime and Y prime into the formula as below to find the R mean. After that, we use the enriching line formula to find the enriching line equation. And the R substituted must be between 1.2 R mean and 1.5 R mean because that is the optimum reflux ratio range. After that, we draw the enriching line connecting XW at 45-degree line to the intersection point between the enriching line and Q line. And starting from top at XD at 45-degree line, we set all the stages until we pass through the XW, and the number of stages are determined. And the right-hand side of the picture is our steps for this chapter with values. Next. We have conducted 2 trials where the first trial is when R is equal to 0.175 and the enriching line equation is determined. In this trial, we have determined the number of trays needed to be 4.4 plus 1 reboiler. Next. For the second trial, when R is equal to 0.219, another enriching line equation is produced, and the number of trays needed this time is 4 plus 1 reboiler, which are lesser. Next, I'll pass the floor to Amalina.
For the conclusion, less number of trays needed when R equals to 1.5 R mean, R optimum 0.19. To cut the cost, R 0.19 is chosen. The number of theoretical trays of the methanol purification unit is 4 with 1 reboiler performed under optimal reflux pressure, which is R optimum 0.19. Location of feed tray is first tray. I will pass to Darwisha.
For the justification, the flow rate of S10 is obtained from the Chapter 2 mass balance, while the flow rate of the S11 and S12 is also obtained from the Chapter 2 mass balance, but conversion from ton per day to kilomole per hour is done by using the high Cs. Flow rate of S11 is through market analysis, which is 3,000 ton per day. The mass fraction of S10 is gotten from the table 1 in problem statement. Mass fraction of S11 and S12 is gotten from the Chapter 2 mass balance. Next, I will pass the floor to Alex.
We would like to thank all the lecturers for the dedication and guidance for this semester. Thank you.
Thank you.
Thank you.